So this video is in 9.3, and as you see on the screen, we're talking about De Moivre's theorem. And when you look at this theorem, you probably look at the word and think, wow, this is going to be difficult. Well, it's not. You've seen the four fundamental, we've been looking at add, subtract, multiply, and divide, and now Abraham De Moivre puts everything together with raising the... It is important, this theorem is important because it allows the last two fundamental algebraic operations, raising to a power and extracting roots, to be used with our complex numbers. Here are some pieces of information which you're going to see in the recording. But in the recording by the author, he does not include exponential. So that's why I'm making this recording, to be able to tie together what you saw for him and then tie it together with the exponential. Remember, and I said this in the very first video I made for 9.3, you have got to be fluent, however you want to see it or say it. You've got to understand complex form, rectangular form, polar form, and exponential form. And you've got to be able to move back and forth between these four very fluently or fluidly, or you got to know what you're doing. And so down at the very bottom, it says, hey, here's his theorem. You need to write this on your part of your formula card that you've deemed your complex area on your formula card. And so as you analyze this, we're going to take our complex number and raise it to a power. And if you look back through here, and he goes over this in the video, that as you see the power, we're going to raise it to the second power. Oh, we're going to raise it to the second power. Oh, wait, we're going to raise it to the second power. Hey, look over here. My magnitude or modulus gets raised to the second power. Oh, wait, my argument gets multiplied by 2. Wow, I wonder if it's going to happen again. If I'm going to the third power, do I raise my magnitude to the third power and multiply by my argument by 3? Yep. Does it happen with 4? Yep. Does it happen with all of them? Yep. And so you need to jot this pattern down, and you may want to write down the formula he has inside the videos too, but you want to put them on your formula card. I'm going to work with us on numbers 5 and 6, but I'm not going to do all of them. I'm going to leave the other part of the exploration, if you will, of example 5 to you, because this is asking for us to do this in exponential and rectangular. He has shown you in rectangular, he is showing you in polar. I want to show you in exponential, and then leave parts of this to you to look for getting exponential to rectangular. I'd rather let you do that and you discover that. So here we are at a complex number. They're asking us to get it in exponential and in rectangular. And so looking at what we have, I'm going to run back over here to the formula. And when I run back over here to the formula, I have to raise my document camera again. I notice that it is saying z to some power, z to any power. Z to any power is going to be the modulus to that same power times e to the I, and then take that number for the power and don't raise your argument to that power, just multiply it by that power. And so that brings us back up to the top over here, that we are looking at example 5. And looking at example 5, do I have an r? Yes. Do I have a power? Yes. Do I have a theta? Yes. Then I'm ready to go. I'm going to be taking this complex number and raising it, as it says, to the third power. I need to take my r and send it to the third power times e to the I, and then right here I need to do 3. I'm going to go ahead and write it 3 over 1 times my argument, my theta, and I get pi over 9. And now I just need to simplify, and that's it. And so I have z to the third power, and 2 times 2 times 2 is 8, times e to the I to the, when we reduce this, we get pi over 3. We are in exponential form. I'm going to scooch right down here and show you we match with the exponential form, and then it jumps straight to rectangular. I suggest that you go back up here and that you go to polar first. And then if you actually evaluate what is the cosine, what is the sine, and distribute the 8, that'll put you right over here at your rectangular. But I'm going to leave that for you to do, and now I'm going to go to example 6. And so looking at example 6, it says use de Moivre's theorem to express what is this to the 5th power in exponential and in rectangular form. And we probably will end up in polar at some point. But right now it's in rectangular and it's to the 5th power. We have our formula, which is z to the n equals r to the n times e to the I times n theta. I'm looking right here. I do not see an r. I do not see a theta. I need to find it. And so that goes back to what we've done earlier in our section to go find r or our modulus. I'm going to take my x and square it, my y and square it, which my y is a 1 hiding right there. And when I do the square root of that, I get square root of 2. And so my r is square root of 2. So in this case, I'm doing z to the 5, and I have square root of 2, and I need to send that to the 5th power, times e to the I times 5 times whatever my theta is. And my favorite is doing the inverse tangent of our y over x. But then also I have to think, what quadrant am I in? And in this case, when I've got 1, 1, 1, 1, that puts me in the first quadrant. And if I have a 1 over a 1, that is screaming pi over 4. And so that's where we're going to use pi over 4. And so I'm putting in pi over 4. I'm going to put that 5 over 1. And let's finish up. The square root of 2 to the 5th is square root of 2 times square root of 2. You get the picture here. But to go ahead and play with it, that becomes a 4. A 2. And that becomes a 2, which there is our 4, times our square root of 2. So we got 4 times square root of 2. So I'm going to pop right back up here. There we are. And I've got 4 times the square root of 2 times e to the. Remember, you can always stop this video, back it up, and watch pieces and parts again. And then right here, we're e to the I times 5 pi over 4. And if we glance down here, about right here, we get 4 times the square root of 2. That's what we had, 4 times square root of 2, times e to the I to the 5 pi, to the e to the 5 I times 5 pi over 4. We match. I'm going to leave the rest of this for you to do because it also says, hey, put your answer in rectangular form. And again, a suggestion is convert this over to polar. Go ahead and write down that, evaluate. What is the answer for cosine of 5 pi over 4 and sine? And that's going to get you right on into rectangular. So this video was talking about 9.3 and working through de Moivre's theorem, specifically using exponential form.